Hello viewers, Wagadaruna taking you through the story of for A-level pure mathematics, and this video I'm going to go through the topic of ellipse, which is under conic sections, and this video is suitable for students in both senior 5 and senior 6 offering principal mathematics as part of their combination. So before we start, let's look at the course outline for this paper. So pure math or math paper 1 is divided into 5 parts. The first part is algebra, where 2 questions come in section A and 2 in section B, and these are the topics. The next part is trigonometry, where 1 comes in section A, 1 in section B, and these are the topics. The third part is geometry, where 1 comes in section A and 1 in section B, and these are the topics. The fourth part is vectors, where 1 comes in section A, 1 in section B, and these are the topics. And the last part is calculus, where 3 come in section A and 3 in section B, and these are the topics. So every topic which is ticked is available on this platform, and at the end of this video you will see end screens which will appear in this form. These are folders, and if you want any video on any of those parts, for example, if I want a video on simultaneous equations, I'll realize it's under algebra, so what I will do, I'll click on this one for algebra. If I want a video which is under calculus, I'll just click on the folder for calculus, and all the videos on calculus will be available. You'll be able to see them. So that's how these end screens are used. And in this video, I'm going to go through the topic of ellipse, which is under geometry. So an ellipse is a conic section whose eccentricity is less than 1. I think you remember that under the video of parabola. So that when the eccentricity is equal to 1, it's a parabola. When it is less than 1, it is an ellipse. And when it is greater than 1, it will be a hyperbola. So in this case, we're going to look at the ellipse whereby the eccentricity has to be less than 1. So let's first draw a sketch of an ellipse. So we have to draw the axes and label them. Now an ellipse is in the shape of something like an oval. So this is an ellipse. Now unlike parabola, remember in parabola there were 3 forms. A parabola can be in this shape, or in this shape, or in this shape, or in that shape. But for an ellipse, it is only and only of this shape. Now in an ellipse, so these are the intercepts. We have an intercept A0, and because this is symmetric about the y-axis, here to be negative A0. And if this is 0b, this will be 0 negative b. So the good thing there's what we need to know in an ellipse, the formulae are also available in your mathematical logbook. So if you check in your mathematical logbook and check for formula 45 under geometry, you'll find this table. This is so this is not supposed to be there. You remove this. So this is an ellipse, and it's our interest. We saw how this column can be used under the video of parabola. So now we are going to look at this column of an ellipse. So we need to know the standard form is in this form: x squared over a squared plus y squared over b squared equal to 1. And the parametric form is this: eccentricity is less than 1, and b squared is equal to this. This squared is got from here, and this is got from there. And then the foci is got from there. Directrices are those ones. So let's first derive this formula. But before that, let's show the foci and also the directrices on our sketch. So just like it was in parabola, directrices are vertical lines. So this is the directrix x equal to a over e, and also this one x equal to negative a over e. So they are similar to the ones in your mathematical logbook. Remember, it was plus or minus a over e, meaning that one is positive, another one is negative. Now we also need to show the foci. So the foci, from this table, it is plus or minus a is 0, Therefore, there are two foci on an ellipse. We shall put the positive one here, and the negative one will be here. Now we have to derive the formula. What we want to do, we want to derive this formula for an ellipse. So what we shall do, we shall consider a variable point on this ellipse, which is point px. And like I told you, from this we can be able to get the eccentricity, because we shall be able to get the ratio. Now this point, this is the horizontal line, meaning that the y coordinates of this and this will be the same, and this line is x equal to this. Therefore the x coordinate of b will be a over e. So that's where those points are coming from. So there are some terms we need to know. One is the major axis and also the minor axis. Now the major axis is the diameter of the ellipse through the foci. So this x-axis is what we call the major axis. Then the minor axis is the diameter of the ellipse perpendicular to the major axis. So this is what we call the minor axis of the ellipse. So this diameter from here to here is the minor axis, and also this diameter from here up to here is what we call the major axis. So we shall start by saying that eccentricity is equal to the ratio of PS to PB. When I cross multiply, bring this on this side, I'll come up with this. I also need to know that, I think I remember the distance between 2 points. So PB is that and PS is that. Then I can put square on both sides to come up with that. So this is 0, that's why here you don't see it there. And this is y squared, this one is that, this one is that. So this is also squared. When you square both sides, this one also has to be squared. And this is what you see here. Then here I've expanded this part. When I expand this one, I'll come up with this in box bracket. When I expand this, I'll come up with this from here up to here. And here what I've done, I've multiplied throughout by this. So when I multiply this by this, it cancels. That's why you see only a squared. This is e. You can see it as e, but there is also a square affixed it. That's why it is e squared over e squared and e squared to give you 1. That's why you only see a squared here. Then this with this, 1 e will remain, and this with this, the whole of e squared will remain. Now next is to collect like terms. When I collect like terms, I'll come up with that, because this and this can cancel. Therefore when I rearrange, I'll come up with that. Then divide throughout by this, I'll come up with that step. Then this one becomes 1. And this one becomes that, because this and this cancels, remain with this alone, and the whole of that remains. Now what I'm going to do, I'm going to let the whole of this denominator to be equal to b. And I think you remember, also in your mathematical logbook, it was there, because here they said b squared is equal to a squared in brackets 1 minus e squared, and that b was got from here. So basically that is what you should remember, that b squared is equal to a squared in brackets 1 minus e squared, and the importance of this is to help you get the eccentricity, because in some questions they will ask you to get the eccentricity of the ellipse. So what you do, you look for a way of making e the subject, as you shall see in the worked examples. So in summary, the equation of the ellipse is this, which I've already seen. Then eccentricity, when I make e the subject, I'll come up with this here. Then foci also is given by this. Remember it from your mathematical logbook. And the directory says are these ones, and the lattice rectum is this, which ends up to be this. So most of them, if you have forgotten them, you can come and refer to your mathematical logbook. Now with that, we shall go through some of the questions. So question 1 says, find the eccentricity, foci, directrices, and latus rectum of the ellipse this. Now this one is not in the shape of an ellipse which you have seen, but can be, because I think we realize that this one is not equal to 1. So what we do, we shall divide throughout by 25 to come up with this step. I think we realize that this one is now in the form of an ellipse, which we know. So now that's in the form, we shall compare it with the general format of an ellipse and be able to get the values of a squared and b squared. So a squared is this, implying that a is that, and also b squared is this, implying that b is that. Now I think we realize that here it was 16 over 25, but here we're saying 25 over 16. Why? Because this is the reciprocal. So to get this is 1 over b squared equal to 16 over 25, meaning that b squared will be the reciprocal, which is 25 over 16. Just as it was here, 1 over a squared was equal to 1 over 25, implying that the reciprocal will be 25, which we wrote here. So you must be keen with that. So now that I've got the values of a and b, we can be able to get our eccentricity. So eccentricity, come and substitute for b squared and for a squared. Remember, b squared was this, then a squared was 25. So in the end, we shall come up with this as the eccentricity. The next is the foci. Foci, remember, is given by this formula. So what I'm going to do, I will substitute for a and for e to come up with this as the foci. The next is the directrices. Directrices are given by this formula, so I'll substitute for a and for e. Then use the calculator to come up with this as the directress. So if you have forgotten these formulas, they are available in your mathematical logbooks as we saw. Then latus rectum is given by this formula, so I'll substitute for a, substitute for e to come up with this as the latus rectum. So now we shall go to general point on an ellipse. So from your mathematical logbook, the general point is this: a cos theta, b sin theta. So what we want to do, we want to see how it comes about. So here what we do, we shall compare this general equation of an ellipse with this trigonometrical identity, which you already know that sin squared theta plus cos squared theta is equal to 1. So what I'm going to do, I'll compare this with this, of course, to come up with this x equal to a cos theta. Then also compare this with the one of sine to come up with this, which is equal to that. So you don't interchange. Therefore, from there, I will say that any point on the ellipse takes the form a cos theta, b sin theta, where a cos theta is the x coordinate and b sin theta is the y coordinate, where theta is the eccentricity angle. So always remember that this is the general form of an ellipse. If you forget it, you can refer to your mathematical logbook under the part of parametric form. So with that, let's go through some of the questions. So question 1 came from UNEB 2003 paper 1 question 14a and says a conic section is given by this and that. Show that the conic section is an ellipse and determine its eccentricity. So here what they want you to do is to eliminate theta in both parametric equations. So what I'll do, I'll come and get this and make cos theta the subject. Also get this and make sin theta the subject. Then from there you remember the identity of this. Then you substitute for cos theta and sin theta. So here when I put the square on each part alone, I'll come up with this expression. Now when you compare this with the general form of an ellipse we know, you realize that this is also an equation of an ellipse. Therefore, you have shown that this conic section is an ellipse. But they also want you to get the eccentricity. So for the eccentricity, you have to first get the values of a squared and b squared. So from here, by comparison, a squared will be this 16 and b squared will be this, which is 9. Therefore, I'll come and say that eccentricity is given by this formula which you already saw. Then you substitute for b squared and for a squared. Then in the end you come up with this as the eccentricity. Then question 2 came from UNEB 2020 paper 1 question 7 and says Roman 1 part A, show that the curve whose parametric equations are this and this represents an ellipse. So this is similar to the one you have just done previously. So what we do, we shall still come and for this make cos the theta the subject, and for this make sin theta the subject. Then remember the identity and substitute. So in the end, this one will be similar to this general form of an ellipse. Therefore, you have shown that this is an ellipse. Then part B, they wanted to determine the eccentricity. So for the eccentricity, you need the values of b squared and a squared. So b squared is this and a squared is that. So in this case, it will be a negative, meaning that there was an error. So always remember that b should be smaller than a. But in this case, b was bigger than a. Therefore, there's no way you can proceed from this step. So you just stop there. And the marks will be distributed accordingly. So next we shall go to condition for tangency. So a straight line this and an ellipse, consider a straight line that and an ellipse that. So when we substitute for y into the equation of an ellipse, this is what you're going to get. So get this one and put it where there is y. You'll come up with this. Then from there, multiply throughout by the LCM. So LCM is a squared b squared. So multiply throughout this gives you that, with this gives you that, with this you get that. The next is to open this bracket. You will come up with this. The next is to collect like terms, x squared alone. This is x squared, so put it alone. This is x, put it alone, and these two also put them alone, so that this side is only 0. Then from there you will compare with the general quadratic equation, which is that, and you realize that capital A is this, capital B is that, capital C is that. So the reason why we are using capital letters, because in this expansion we have, there is small a, small b, and small c. So there is no way you can put here that small a is equal to this. That will be confusing. So that's why you use capital letters. Then from there you shall remember that for tangency, the discriminant, this is the discriminant, will be equal to 0. So what you are going to do, we are going to substitute for b, for a, and for c, and simplify that. So let's do that in the next slide. So substitute for b, for a, and for c. Then expand and simplify. So in this case, this and this can be combined to give you this. Then this one is here and this one is there. And what I've done, I've taken the whole of this on this side. Then from there, you'll realize that something can cancel. This 4 can cancel. This a squared can reduce this to become a squared here. That is why you see here a squared. This remains, this remains, this remains, and this remains. Then next is to open these two brackets to come up with this. Then from there realize that this and this can cancel. That's why here there is 0. And here there is this remains, and that remains. Then you can take this, you can take these two this side to come up with this. Then from there realize that b is common, so this can cancel with this and also reduce this by 2. That's why you see b squared there. And basically that is the condition for tangency. And this m is called the gradient of the tangent, because the tangent was y equal to mx plus c. mx plus c. So this is the gradient of the tangent, and this is the y-intercept. So with that, let's go through some of the questions. Question 1 says, question 1 came from UNEB 2018 paper 1 question 15 and says, the line y equal to mx plus c is a tangent to the ellipse this. Part Roman 1, obtain an expression for C in terms of A, B, and M. So this is exactly what we have done. So we shall just go through it first. So given that, you are going to substitute for Y, then cross multiply by the LCM, expand this. So these procedures are always the same, and also the output will be the same. That is why I'm just going through it, perusing through it first. So all these ones, they are the same. Then for tangency, you remember that discriminant is equal to 0, substitute for B, A, and C. Then do the same, take this one this side to come up with that. Then reduce, divide by 4A squared. Then also from there, expand this. Then from there, this will cancel. So the procedure is always the same. Take this one this side, then reduce by B squared to come up with this. So everything has been the same as we derived it under the condition for tangents, and this you have to be conversant with it, because most of the questions on an ellipse, they will tell you to prove that condition for tangency, as we shall see in the questions to come. So part B says calculate the gradients of the tangents to the ellipse through the point this. So the x coordinate is this and the y coordinate is that. Now the good thing we have already derived this, that c squared is equal to that. Therefore at point this, it implies that x is that and y is that. Therefore what I'm going to do, I'll come and substitute. So come here and say that from this equation of the tangent, y is 0, x is this, and c, remember we have saw that c squared is equal to this, so c is the square root, but it has to be plus or minus here, because square root gives you plus or minus. Always remember that. So take this one this side to come up with this negative, then square both sides to come up with that, then open brackets to come up with that, and simplify, because when you simplify, this will cancel with all this, so the whole of this will cancel, remain with this which is there. Therefore this will also cancel to remain with m squared equal to 1. Therefore m will be plus or minus 1. So these are the gradients of the tangent. Then question 2 came from UNEB 2000 paper 1 question 6 and says show that the line this is a tangent to the ellipse that. So still the procedure will be the same, only that in this case they have given you values instead of unknowns. So we shall do the same from this equation of the tangent, from this equation of the line, make y the subject, then come to the equation of the ellipse and substitute for y. After that you expand. So when I expand this, I'll come up with this. So this 36 is because this is 9 times 4, because this was 2 squared to give you 4, 4 times 9 to give you 36. Then multiply through by the LCM to come up with that. Simplify to get that quadratic equation. Now they told you to show, therefore you have to remember that for tangency, or for the line to be a tangent, the discriminant must be equal to 0. Now here I'm using small letters because in this quadratic there's nothing like small a, small b, or small c. But if they were there, here I would have used capital letters to distinguish the two. So substitute for b, substitute for a, substitute for c. Then simplify, you'll come up with that, and 0 is equal to 0, which is true, and because it is true, it implies that this line is a tangent to this ellipse. So that is how they show. Then question 3 came from UNEB 2003 paper 1 question 14b and says given the line this and the tangent this, show that this is equal to that. I think you see what I've told you, that always this condition is very common in the questions of an ellipse, so you have to know how to derive it, the condition for tangency. So hence determine the equations of the tangents at the point this to the ellipse that. So this first part is very similar to the condition for tangency. So what we are going to do, we are going to just peruse through it. So this is the equation of the tangent, substitute for y, then multiply through by the LCM, expand this. So the procedures are always the same. Then do that. So collect like terms. After collecting like terms, you come here and remember that for tangency, discriminant is equal to 0. Substitute for B, A, and C to come up with that. Then take the whole of this side to come up with that. Then reduce by 4a squared to come up with that. Open this bracket to come up with this. And this cancels to come up with that. Then take the whole of this side to come up with this. Then reduce by b squared to come up with this. So the procedure will always be the same. That is why I'm just perusing through. Now what our interest is this hence part. So the hence part says, hence determine the equations of the tangents at the point this, -3, 3, to the ellipse this. So in this case, they have given, you can be able to get the value of b, because okay, a squared is this 16, b squared is 9, and the point is this. So you come and say that for the hence part, we are given this, implying that by comparison we shall be able to get the values of a squared and b squared. Therefore, using this point on the tangent, remember the tangent was y equal to mx plus c. Therefore, substitute for y and for x to come up with that. But I also, therefore, from here, when I make c the subject, I'll take this one this side to come up with that. Now, from this equation which we have derived, I'm going to substitute for c, for a squared, and for b squared. So come and put c, put this one here. Then also a squared is here, so come and put it there. B squared is here, come and put it there. Expand to come up with that. So the good thing now, I have an equation with the only one unknown, which is m. So simplify, I'll come up with that. Factorize, come up with that. Therefore, m is equal to 0 or m is equal to 8/7. So the required equations of the tangent are given by, so remember this is the general equation, so I'll have to substitute when m is 0 and also when m is that. And I also remember the expression for c, so here I'll come and say that c is that. Therefore, when m is equal to 0, I'll come up with this. So substitute for m here, 0, 0, you remain with 3, therefore y will be equal to 3. So this is one equation. Then when m is equal to 18/7, I'll come and substitute here for m, here and here. And I'll come up with this as the second equation of the tangent. So now we shall go to question 4, which came from UNEB 1990, paper 1, question 6, and says, show that the two tangents of the gradient m to the ellipse this are this. Then find Roman 1, the equation of the tangents to the ellipse this from the point this. Then Roman 2, the coordinates of the points of contact of these tangents. Now if you look at this, it is similar to the one of deriving the condition for tangency, because especially they wanted to show that c is equal to that. So let's also peruse through it, that part of condition for tangency first, then we go to Roman 1. So here we shall come and say that let the equation of the tangent be in the form that, because it wasn't given the question. So I'll come and write the general equation of the ellipse and substitute for y. Then multiply forward by the LCM to come up with that, or expand this to come up with this. Then collect like terms to come up with the quadratic equation in x. Therefore, for tangency, the discriminant is equal to 0. So all these ones we have already seen under condition for tangency. So come and substitute for b and c to come up with that. Then take the whole of this side to come up with that. Then reduce by 4a squared to come up with that. Then expand this to come up with that. Then cancel this to come up with that, and take this one this side to come up with that, then reduce by b squared to come up with that. Therefore, we shall conclude that from this, the equation of the tangent is this which was required. So now we shall go to this Roman. They said, find the equation of the tangents to the ellipse this at from the point this, not this side, from the point this. Therefore, we can get the values of a and b given the ellipse. So you come and say that given this ellipse, by comparison with the general equation of an ellipse, a squared is this, b squared is that. Therefore, from this equation of the tangent, I'll come and substitute for a and for a squared and b squared to come up with that. Then at this point, x is -2, y is 5. Therefore, come and substitute for y and for x. You'll be able to come up with this. Then you square both sides to come up with that. Now the good thing, I have an equation with only m, therefore I can easily get the value of m. So get the quadratic is that I can choose to reduce, but to get that then use bulldozer method, or factorization by bulldozer method is easier. To come up with the two values of m will be -1 and m is equal to 11. Now from this equation, I'll come and substitute for each value of m. So when m is -1, come and substitute and be able to get that equation. Now there are two equations of the tangent in the for m equal to -1. What about for m equal to 11? So I'll come and say that for m equal to 11, I'll come and substitute for m, then be able to come up with also two equations. So we have got 4 tangents, but they only need 2, so the required tangents must pass through this point. Therefore, we start by testing. For this equation, for this tangent, it must satisfy this point, so let's see if it satisfies. Where there is y, put there 5, where there is x, put there -2 to come up with this, which is true, so that tangent is required. What about for this other one? For this other one, when I substitute, it is false, meaning it is not required. Then for this one, when I substitute, I'll come up with this, which is required, and for this other one, when I substitute, I'll come up with this, which is not required. Therefore, the two tangents are this and that. So we shall come and conclude that the required equations of the tangents are this and that. Now we shall go to tangents and normals to an ellipse. So given the ellipse this, the equation of the tangent and the normal to the ellipse at the point this, remember this is the general point of an ellipse, can be got as follows. So given the ellipse, you have to differentiate to get the gradient function. So when I differentiate and make dy dx the subject, I'll come up with that, and that will be my gradient function. So I'll come and use that at this point, x is equal to this and y is equal to that. Then when I substitute, I'll be able to get the value of the gradient of the tangent. So substitute for x and for y to come up with this as the gradient of the tangent. Now I have a point and the gradient, meaning that I can get the equation of that tangent. So this is the gradient using the variable point xy and this point general point. Then this is the gradient which you have already got. Cross multiply, I'll come up with that. Expand, I'll come up with that. Collect like terms, when I take this on this side, I'll come up with this. Then I remember that the whole of this is equal to 1. Therefore, this will be the equation of the tangent to an ellipse. So that was the tangent. What about the equation of the normal? So what we need to remember is that the normal and the tangent are perpendicular to each other. That means that the gradient of the normal is a negative reciprocal of the gradient of the tangent, so it will be given by this. Now using this point and the gradient, I can be able to get the equation of the normal. Using this formula, change gradient using the variable point xy and this general point, then here this is the gradient I've already got. Cross multiply, I'll come up with that, open brackets, I'll come up with that. Then you collect like terms so that you put on y on one side, and that will be, so here what I've done to move from here to here, I have divided through by cos. So when I divide through by cos, this one cancels, and this one sine over cos gives you tan, and this one, this cos cancels, you remain with only sine. And that will be the equation of the normal. So with that, let's go through some of the questions. Question 1 came from UNEB 2009, paper 1, question 15, and says, Roman part A, find the equation of the tangent and the normal to the ellipse this at the point this. So let's start with that. So the procedure will be always the same. Get the equation of the ellipse, differentiate, so that we can easily get the gradient function. So when I differentiate, that will be the gradient function. Then from there, I remember that my point x is this and y is that. So I can substitute to get the gradient of the tangent. So at this point, x is that, y is that, therefore the gradient of the tangent will be given by this. So now I have a point and also a gradient, therefore I can easily get the equation of the tangent using this formula. Then cross multiply like we did before, open brackets, then collect like terms like this one this side, then you remember that this one is equal to 1. Then for the equation of the normal, we have to get the gradient of the normal, which is the negative reciprocal of the gradient of the tangent, and it will be given by that. So come and substitute. So using this point and the given gradient, I can easily get the equation of the normal using this formula. Cross multiply to get that, open brackets to get that, collect like terms to get that. Because when this one goes this side, it will be negative 4 plus 4 to give you negative 3. Then divide through by cos theta to come up with that. So now shall go to part B. So part B says, if the tangent in A cuts the y-axis at point A, know this word y-axis at point A, and the x-axis at point B, and the normal cuts the x-axis at point C, find the coordinates of A, B, and C. So for the tangent, we need to get the y-intercept and the x-intercept, and for the normal, they said cuts the x-axis at the point this, we need to get the x-intercept. So let's first make a sketch of that ellipse so that we can easily interpret the question. So I'll have to draw the axes and label them, label the x-axis and also label the y-axis. Always remember that. Then draw the ellipse. I told you the ellipse is always of one shape, which is an oval. Then we need a tangent at this point, so we shall draw that tangent so it cuts this y-intercept at that point A and also this x-axis at that point. Then we also need to draw the normal at that very point to cut this x-axis at this point. So those are the 3 points they want. So for the tangent, we know that this is the equation of the tangent. Therefore, when x is equal to 0, I'll come up with that. Therefore, y will be that, implying that point A is given by that point. Then when y is 0, I'll substitute to be able to get the value of x, therefore point B will be that. Now for the normal, this is the equation of the normal, so I'll come and substitute. When y is 0, I'll come and be able to get the value of x, and x will be that. Therefore point C is given by that, and that's what they wanted. So question 2 came from UNEB 2004 paper 1 question 13 and says, part A, show that the line this is a tangent to the ellipse that. So let's first show. So we shall follow the same procedure, make y the subject and substitute for y in the equation of the ellipse to come up with that. Then expand to come up with that. So when I expand this, I'll come up with this. Then multiply throughout by the LCM to come up with that, then get the quadratic equation, and you can reduce the quadratic equation. Then from there, remember that for tangency, discriminant is equal to 0. So for tangency, the discriminant is equal to 0, so come and substitute for B, A, and C, and come up with 0 equal to 0, which is true. Therefore, the given line is a tangent to the ellipse. That was part A. What about part B? Part B says, find the equation of the normal to the ellipse at the point of contact. So we have to first get the point of contact. So the normal to the ellipse, first of all, the gradient of the tangent is 4/5. Therefore, the gradient of the normal is the negative reciprocal of the gradient of the tangent, which is that. Now from this one, I'll be able to get the point of contact, which is the x-coordinate. So come on, this is a quadratic equation, so I can use bulldozer method, and I already know that the whole of this discriminant is equal to 0. Therefore, I'll come up with the value of x as -4. Now when x is equal to -4, I'll come up with y as that. So that is the point of contact. Therefore, using this point of contact and the gradient of the normal, I can be able to get the equation of the normal from that. So when I take this one this side, I'll come up with that. Simplifying gives me this, and therefore the equation is that of the normal. Then now we shall go to part C. Part C says determine the eccentricity of the ellipse. So from this equation, if I compare with the general equation of the ellipse, I'll realize that b squared is this and a squared is that. Sorry, a squared is that and b squared is that. Therefore, the eccentricity is given by this formula. I think remember it, so substitute for b squared, a squared to come up with this. And that's what they wanted. So now we shall go to ellipse involving loci. So we already covered the topic of loci, and in this case, there's nothing to talk about under loci. So what we need to do is to go through straight to the worked examples. So question 1 came from UNEB 1989, paper 1, question 11b, and says, the normal at the point this on the ellipse this meets the x and y axes at A and B respectively. The midpoint of AB is capital M. Show that the locus of M is an ellipse. So in under ellipse, for you to get the locus, you have to eliminate theta. That's the only condition for you to get an ellipse. So let's first make a sketch of the information given. So we shall draw the axes and label them. So we have to label the x-axis and also the y-axis. Then draw an ellipse. Ellipse will always be of the same shape. So this is the point where we shall draw our tangent. And also we shall draw our normal from there. So there is this point A, and there is this point B, and there is this midpoint capital M. So from this equation of the ellipse, when I differentiate, I'll come up with this. My aim is to get the equation of the tangent and also for the normal. So the gradient function will be given by that. Therefore, at this point, x is this and y is that. Therefore, substitute to get the gradient of the tangent. After getting the gradient of the tangent, that is when I can get the gradient of the normal. So gradient of the normal is the negative reciprocal of the gradient of the tangent. Now using the point this and the gradient of the normal, I can be able to get the equation of the normal. From this expression, I will come and cross multiply to come up with this, open brackets to come up with that. Collect like terms, take this one this side, so negative 16 plus 9 gives you negative 7. Divide through by cos theta to come up with that. So this is the equation of the normal. Now when y is 0, I can get the value of x, which is that, implying that point A is that. When x is equal to 0, I come and substitute to get the value of y. That implies that point B is that. The midpoint of AB is got by getting the average of the x coordinates and also average of the y coordinates. So average of this is that, average of this is that. That implies that capital X is equal to this and capital Y is equal to that. Therefore, remember I told you the locus means that you have to eliminate theta. So here I have to make theta cos theta the subject. And from this Y I also make sin theta the subject. Then I remember the identity for this Pythagoras. Therefore, I come and substitute for cos theta and also for sin theta. Open brackets to come up with that. Therefore, this is the locus of the midpoint AB. So locus for ellipse, you have to eliminate theta. That's the simple condition. Then question 2 says, the tangent to the ellipse this, at a point this, meets the minor axis at A. If the normal at P meets the major axis at B, find Roman 1, the coordinates of A, Roman 2, the coordinates of B, and Roman 3, the locus of the midpoint of AB. So let's first make a sketch. Draw the axes and label them. Then from there you shall draw an ellipse. So the ellipse is always of the same shape. So this is the point which you are given. Then you shall draw a tangent. So it means this minor at A and also the major and the normal meets the major axis at B. So they want you to get the coordinates of A, B, and also the locus of the midpoint AB. So given this equation, differentiate to come up with that. Therefore, gradient function will be given by that. Now at this point, x is this, y is that. Therefore, substitute to get the gradient of the tangent. Now using this point and the gradient of the tangent, I can be able to get the equation of the tangent using this expression. I'll come and cross multiply. I'll come and make, my aim is to make y the subject. So take the whole of this side to come up with this. Then take also this one this side, that's why there is plus that. Now when the tangent P at P meets the minor axis, x is equal to 0. So when x is equal to 0, substitute for x and be able to come up with this. So in the end, you shall come up with the value of y as that. Therefore, A is equal to that. For point B, we need the equation of the normal. So the gradient of the normal will be given by that negative reciprocal of the gradient of the tangent. Therefore, using this point and the gradient of the normal, I can be able to get the equation of the normal using this expression. Therefore, I'll come and cross multiply, expand, simplify, and then come and say that when the normal meets the major axis, y is equal to 0. Therefore, substitute for y and be able to get the value of x. When I get the value of x, it implies that b will be given by that point. So I have 2 points. I have to get the locus of the midpoint. So I have to first get the midpoint of AB, which is the average of the x coordinates and also average of the y coordinates. That means that x is equal to this and y is equal to that. So come and equate the two, equate x to that and y to that. But remember, I have to eliminate theta, so from this step I have to make cos theta the subject, and also from this I have to make sin theta the subject. Then from there I'll use the identity, substitute for in that identity, expand, cross multiply or multiply by the LCM to come up with that. You can choose to rearrange or you stop there, and that will be the equation of the locus of the midpoint. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on hyperbola. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on hyperbola has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.